Alright, so chapter 2 is due today, folks. Any questions on the chapter 2 homework? Where the question was perhaps a little bit vague, you're not entirely sure what it asked, or anything like that?
2.110.
Which one is that one? So it asks you to calculate the cumulative frequency?
We have to do like the whole table, right? For 2.1?
Well, not all of it. So the last two problems, yes, but number 10 was just calculate the cumulative frequency for the table that they gave you. I mean, you can still do all of the whole thing if you wanted to for that particular one. That would have been okay. But all I really wanted was the cumulative frequency column of the full, big, huge, blown-out table. Every time it says do it all the time?
Pretty much.
Well, it's good practice. So what do you do when you try to find cumulative frequency, folks?
I don't know.
Right. So basically, just add the row frequencies as you go through the columns. Hey Ben. Oh no, it's quite all right. You made it. Yes.
So one of the pie graphs, were we only supposed to find the percentage of the things that were in parentheses? Or were we supposed to like think outside the box?
How do you mean?
So it was like, what percentage of Shelley's budget is spent on household bills? And then they would give you stuff in parentheses? I guess, are those just, is that what we find, or is it like, is that just like we can?
No, I'm pretty sure then you're just supposed to do what it's supposed to say, right? I mean, it's not trying to trick you, in other words, right? I mean, so what number was that one? 22. Right. So, I mean, the percentages is just telling you what categories that particular item represents. So, for like part C, where it says what percentage of Shelby's budget is spent on household bills, they just want you to. They're telling you that household bills are housing, utilities, cable, and cell phone categories, and the table next to it. That's all it's telling you. So it's not trying to make you think of other categories or something like that. No, it's just telling you those are the 4 categories to use to answer this particular question. Otherwise, chapter 2 was relatively okay. All right, well, if you're happy, I would love to have your Chapter 2 homework. You are more than welcome to turn it in on Wednesday. As long as you turn it in before class starts, we're all good. And Monroe, folks, I will try to get your homeworks out to you sooner rather than later. I may try and put them on the bus for class on Wednesday, but we'll see.
So, do you have the second edition's book?
I just have the second. Yes, I have the actual second edition. Yes.
Okay, because for problem 22, I couldn't really see your pie chart because it was in black and white.
Okay.
So I did it from my problem, which was 26 in the book.
No problem. All right, so on to new stuff then. So. So, chapter 3. Okay, so section 3.1 in chapter 3 talks about measures of central tendency, which is a phrase that if you say, you must say in the snootiest possible, way that you can, because it just sounds like a snooty phrase, measures of central tendency. So the idea here, though, is that in 3.1, when you are measuring something, why do you try to figure out what a central tendency measure is? So, first off, what are the measures of central tendency? I assume you guys probably have heard these three terms before. Mean, median, mode. What's the mean, folks? The average. Why do statisticians call it the mean instead of the average? Yeah, that's absolutely right. If you say the word average, folks, what does it sound like? Yeah, it kind of sounds like what it sounds like, average. But if you say the word mean, what does it sound like? You're saying something that's important, it's short, it's quick, it's meaningful, it's a great word, right? And on top of it, it makes statisticians sound tough, right? Because they're mean. We always work with the mean. I mean, as a statistician, you're generally not the most physically intimidating person in the universe, so you try to come up with terminology that makes you seem perhaps a little bit more intimidating than you are. That's, of course, just me making stuff up. I honestly have no idea why they call it the mean. I would call it the average, but they like to call it the mean, so that's what we call it. Okay, so whatever. Just realize that when we talk about the mean, we're talking about the average. Now, how do you calculate the mean? Add up the numbers, divide by the number of numbers, right? Okay, so it is exactly what you think it is. Now, one of the things that you do need to get in the habit of dealing with when talking about the mean is notation. When you are dealing with statistical variables, like X or Y or Z or A or B or whatever, whenever a statistician puts a bar over a variable, they're implying that this is the mean of that variable, okay? So, in theory, right off the bat, as soon as you see a letter with a bar over it, you know what that letter with the bar over it means. It means the average, okay? It's just a standard notational factor that statisticians use, and you kind of have to get in the habit of working with it, all right? Now, one of the other things that you have to work with is the definitions of things written the way statisticians and mathematicians like to write them. Okay? So I'm going to write for you the mean as written by a statistician or a mathematician. That is how a math guy or a stats guy will write how you calculate the mean. Now, what the hell is all that chicken scratch? Alright, so what's this weird thing right here? Does anybody know what that is? It does look like a sideways W if you think about it, if you look at it a little bit. It's the Greek letter sigma, right? This is actually a Greek letter, sigma, right? If you've ever looked at like the fraternity butts, right, on their sweatpants, right? You may have seen this symbol up there. It's a sigma, all right? So you learn a little Greek in this class, whether you like it or not. And does anybody know what that symbol means? Yes, it's summation notation. So whenever you see that little symbol, that basically means add these things up, all right? So the idea that about the x with the little sub I on it, that's just telling you add up all of the values inside the variable x. And then guess what n stands for? Number of total numbers, yes. And that is also relatively standard notation in almost all statistical studies. Whenever you see little n, that's the sample size, okay? Or the number of numbers that you've collected in your data set. All right, so basically what this little math symbology means is add up all of your variables x, i.e. add up all of your numbers, and then divide by the total of your numbers, or the number of your numbers. Hence, it's the exact same thing that you think it is, the average, okay? But that is very common notation. Statisticians will use summation notation on a regular basis. So when you start seeing this Greek letter sigma, folks, from now on, your brain has better start thinking add instead of Greek. And hopefully, you've all seen this symbol somewhere before in your lives, right? I mean, besides at a fraternity house or something like that, right? Where have you seen this symbol otherwise, other than in here and in a fraternity house? It's not quite E equals MC squared. Where? Monroe, folks? Where does this exist other than in this class? It's often used in physics too. All right, just to be safe. I'm going to fire up Excel really fast, because if you've played with Excel at all.
Can you not hear us? Or we not hear them?
Are you guys saying things over there and I can't hear you?
Yeah, she said Excel for a while now.
Oh, okay. You got to speak up, Haley. We're mostly deaf over here. I turn the volume down so that I don't necessarily hear the people out in the hall before things start. So yeah, there's a button right here, right? The auto sum button. That's a standard button in Excel that basically says add numbers up. It's using the same symbol, that Greek sigma that says add stuff up. All right, common sort of practice to deal with adding values up. All right, so again, notation that we will use again later on, so it's good to get used to it now because we're going to play around with it more in a little bit. What's the median? course, is what you don't drive over when you're on the road because it leads to head-on collisions, and that's bad. So yeah, it's the number in the middle. Now, why do there have to be two cases?
Because you can have one that's directly in the middle, or you can have two that are both like both.
Sometimes you have a number in the middle, sometimes you don't. What's happening when you don't have a number in the middle? There you go, yes. So the two cases you have for dealing with medians is when you have an odd number of numbers and when you have an even number of numbers. When you have an odd number of numbers, find the n plus 1 over 2th number. Basically what I'm giving you is the position of that number that is in the middle. And if the number is even, average the two middle numbers. So in this case, there isn't a unique number in the middle. There's actually two numbers in the middle, and technically you average those two numbers to determine what your median is. And again, the positions of those median numbers are n over 2 and n over 2 plus 1, which we'll talk about in a little bit when we get to some examples. All right? So, really quickly, just to be safe, if I gave you that set of 7 numbers, what's the median? Okay, good. I gave you this set of numbers. What's the median here? So note, a lot of times people can sort of assume that the median is always a number in the set. Please note that it may not be if the number of numbers you have is even, right? So in this case, the two middle numbers are 8 and 10. The average of 8 and 10 gives you 9. Okay? So, now, when we get to larger examples, I will sort of try to explain what those little notations are for finding them. But the idea behind it, when n equals 7, folks, what is 7 plus 1 over 2? Eight is the fourth number, okay? So that's what that n plus 1 over 2 means, is it's the position where you will find the middle, okay? And likewise, for this example over here where n was equal to 8, what's half of 8? Fourth and fifth numbers, right? 8 is your fourth number, 10 is your fifth number. Average those two together, there's your median. It gives you a quick way of finding where the median is if you can't immediately see what the median is, okay? So right now, it's easy to see what the median is because you've only got 7 or 8 numbers, so you line them up and you can tell. But if there's thousands of numbers, how do you figure out which one is in the middle? You're going to use that trick to find it for yourself, okay? Or at least find it a little bit faster anyways. All right, so, again, we'll come back to that in a little bit. And then last but not least, what is the mode? Oops. It's the most frequently repeated number, or I will say data. Because remember that some of the information you gather when you're doing statistical studies is not numerical. There are some conditions with the mode, folks. If in your data none of the elements inside of it repeat, then technically the mode is that there is no mode. And please note that that is different than saying 0, because 0 is a wonderfully nice number that can repeat. So please don't write down 0. Write down the phrase no mode or none if asked. You can also have more than one mode. If more than one data value repeats most frequently. So you can be bimodal or trimodal, or if there's even more than 2 or 3 of them, you could be multimodal. So let's suppose we had this set of data. What's the mode of this set of numbers? One, 3, and 5. And don't do anything with the 1, the 3, and the 5. Just give them to me all as separate values. In other words, don't average them, don't add them, don't multiply them, just they're all the mode. Tell me that all the numbers are the mode. That's perfectly okay. All right? Not bad with the 3 M's? Okay. Now, some additional pieces of information about this. You may sometimes be forced to calculate a weighted mean. Why in a school classroom would we care about weighted means? What is the most classic weighted mean that we calculate at the end of every semester? GPA, folks. GPA is a weighted mean, right? So, well, let's just... All right, so let's assume that these were your grades last semester. Okay, so let's suppose that you got an A in your 1 credit, what's the student success class, is that what it is? Yeah, so you basically went to class every day, so they gave you an A. Yay! You also got an A in your psychology class, which was 3 credits. Unfortunately, you got a B in your physics class, which was 4 credits. And then suppose unfortunately that you got a C in your, economics class, because you just really hated the econ class you took. I didn't teach it, so you thought it sucked. I totally understand. So, but you still passed because you would never fail a class. Okay, so my question to you is, what is your GPA for this semester? Where, again, assume A is 4, B is 3, C is 2, D is 1, and F is 0, point-wise for your grades. How would you guys do it? Well, don't you guys check the school to see if they're giving you the right GPA at the end of the semester? This is good then. I'm glad I'm showing you this, right? So your GPA. So the way it works, if you want to figure out a weighted mean, so let's call it W bar. So your weighted mean is the sum of your data times your weights divided by the sum of your weights. Now, my question to you folks is which one of these is your data and which one is your weight? Which one is X and which one's W?
Credits are your weights and grades.
Grades are your W, grades are your X's, your credits are your weights, because the credit is how strong the grade really is, right? Because if you're spending 4 hours a week taking a particular class, that letter should be worth more than if you're spending 3 hours a week, and hence the weighting of the particular grade. So in this case, how would we calculate our GPA? Well, an A is 4 times 1, because it's 1 credit, plus 4 times 3, because it's 3 credits, plus B, which is 3 times 4, plus 2 times 3, all divided by 1 plus 3 plus 4 plus 3, right? And there's a quick application of that summation process, or that summation notation concept, so that you can kind of get a feel for how it works, right? So 4 plus 12, 16, plus 12, 28, plus 6, 34. 4 and 4 and 3 is 11. So what's 34 divided by 11?
Like 3.1.
3.1 something?
Well, 3.09.
3.09. So even though it looks like your GPA should be way, way, way above a B because you've got 2 A's, a B, and a C, unfortunately it's not quite so much because that A was only worth 1 and the B was worth a little bit more at being 4. So again, that's the idea behind calculating GPAs or calculating any sort of weighted mean for that matter. All right? Not bad? All right. So another way that you have to calculate weighted means. Grades are X's, the credits are W's. All right, so folks, back when I used to teach economics, I used to give every week a 6-point quiz. That was my process, okay? It was also kind of how I kept track of attendance. Since econ classes always had like 30 students in them, it was sort of a pain in the butt keeping track of all 30 students. Some of them would leave, some of them would come, blah, 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 blah. And so basically what I told students was, if you took the quiz, I counted you as attending, and if you didn't, then I said you weren't. Sort of a double whammy. But the quiz was six points. And I used to create these frequency tables to describe my data, right? So possible scores on the quiz were from 6 down to 0. And here was the range of scores that I had. So one semester where I had, say, like 30 or 60 some students in this class, these were the quiz scores after a certain amount of range. 25 sixes, 51 fives, 22 fours, 12 threes, 6 twos, 3 ones, and 19 zeros. Of course, the reason I had 19 zeros is that if you didn't show up for the quiz, you got a 0, right? So when students were absent, if they didn't give me an excuse that I considered to be worthwhile, I was just like, okay, you got a 0 this week, move along. All right? So, what's the mean of my quiz scores, folks? How'd you figure that out?
I added up all the frequencies and then I multiplied the frequencies by the score and added together the score times the frequency for each of them, divided it by the total frequency.
All right, so first thing you did was added up the frequency. What were all the frequencies? So note, $138, that's the number of quizzes that I gave, right? It's our data element. Folks, this is also the sum of my weights, right? The frequency is W, my score is the X. So how do I calculate weighted mean? I multiply these things across, 150, 255, 88, 36, 12, 3, 0. Add those up. What did that add up to?
543.
And this is exactly what we just did for GPA. It's just now in a frequency table of data for quizzes, right? So this sort of concept of weighted mean, it can be just a regular mean where you're given a frequency table and the frequency drives the weight, or how many times did this number repeat? Same sort of concept, okay? And sorry, what did you say that worked out to be approximately?
3.93.
3.93? Yeah, the zeros are what killed me, folks. If you think about it, 4 out of 6, that's like a maybe a C if you're lucky. So now, what's the median of my quiz scores? 5? Why 5? So that's the mode. 3. Is it 3? Because 3 is the number that's in the middle. Remember what this means, right? What does it mean to have 25 sixes? 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6. Do you want me to keep going? No, right?
Would you take 138 plus 1 divided by 2? Is that what you want? Or are you looking for?
When it's even, what are you looking for? What did my notes say back on the last page? Yes, 2 pages. n over 2 and n over 2 plus 1. What's n over 2, folks? What is the 69th and 70th numbers in this list?
Both fives.
Both 5s. Because technically, right, what are your first 25 numbers? The first to the 25th numbers are 6s. The 26th to the 76th numbers are 5s. So the 76th number is a 5. What does 69 and 70 have to be? 5s. How do you average 5 and 5? 5 plus 5 over 2 is 10 divided by 2, or 5.
I was right in one way.
You were right. And if you could have explained it, I'd been like, sweet, that's good work. And then last but not least, what's the mode of this data? This is also 5 because that had the number that repeated or had the largest frequency the most. When you get a frequency table, finding the mode is sort of like, can you see me? It's almost like a freebie. Just be careful. I'll sometimes have students tell me that the mode for this particular problem is 51. Why would they say 51? Yeah, because they give me the frequency of the largest number instead of the data associated with that largest number. So be a little careful with that one, just don't make that mistake. Alright, not bad though? And it's kind of nice, right? Having the ability to find that median without having to write all of the numbers down, right? Even though there were 138 of those numbers, in order for us to find the median, didn't take much work as long as we remembered the little mini formulas, n over 2 and n over 2 plus 1, right? So, my question to you guys is, which one of those 4 numbers should we use as the measure of central tendency for this quiz? I mean, what's the mean, basically, if we round it to the nearest whole number? 4, but my median is 5. For a 6-point quiz, it's kind of a big difference between 4 and 5, right? So which one is it? Is the middle number 4 or is the middle number 5? You're taking the average on the 4, I agree. But which one's the right number to call my measure of central tendency, right?
That's how good you want to look.
Amen. And note, folks, this is where you start learning how to lie truthfully, right? Because if I wanted to point out that I actually give out nice, easy grades, and that I'm an easy teacher, I would say, well, the median of my quizzes is a 5, which means that basically the middle of score is a medium to high B. If, on the other hand, I want to sound like a hard-ass teacher, like I'm a real mean teacher, I can say, hey, the average on my quizzes is about a 4, which is more like a D or a C. And either of those ways of depicting my middle central tendency number, both truthful, but they can both be used to show a different side of my teaching capabilities. So I'm not necessarily lying with either of those pieces of information. I'm just showing you the side that I want you to see. And this is a very, very common practice when dealing with statistics, is that they show you the numbers that are truthful, but then don't bother to show you anything else that might in any way, shape, or form contradict what we as a person showing the statistics want to show you. So, again, it's one of those things where I just want to make sure you know. And note, folks, that this is not really deep math here at all. I mean, this is nothing deep in any way, shape, or form. I'm not doing a whole bunch of complicated math to try and hide stuff from you. All I'm doing is giving you the information that makes me look the way I want me to look, okay? In theory, if you have someone reporting either the mean or the median, you should always ask for the other piece of data, period. If they're only reporting one of them, it's almost a guarantee that they're hiding the other one for a reason. Ask for it, okay? So if someone tells you that the average salary in the United States is like $46,000 a year, you can say, great, that's the mean, what's the median? And someone will have to report back to you $31,000 a year. And what does that mean if the average is 46 and the median is 31? Yeah, there's way more people down there at the lower levels than there are way the hell up there in the quadrillion billionaires, right? There's enough billionaires to offset all of these people that are making between $20,000 and $30,000, so the average is all the way up there at 40,000 bucks, right? And that's the same sort of thing that's going on here in my data, right? I have slightly skewed data. It can look like I'm giving nice, easy grades, but if I don't want it to, I can switch the statistic and show you the one that makes me look hard-nosed instead. And that's very common, okay? Especially when you have data that's going to be skewed, all right? So, again, just be careful with that kind of stuff and realize that when the mean and the median are relatively close, that's when you have data that is generally considered to be either uniform or more normal. Okay? Now, that doesn't necessarily mean that the data is good and or bad. It's just giving you information about the data behind the numbers. And you want to know those things so that you can use it to, inform yourself about what's going on. All right, so anyways, I'll rattle on forever if you don't watch out too much. Now, why is the mode a central tendency measurement? True. Why is that of any importance?
Because, like you said, with the money situation, you're always gonna have people. So it's by grade wise, you can have some people that are always straight A's, but then you have your people at the bottom that kind of offset curve with the low grade, and then there's people in the middle. And there's a lot of people in the middle that kind of shows what the class average, not average, but the class has the most grade.
Yeah, it's not, you're not too far from, you're not wrong, let's put it that way. But in general though, if you're working with numbers, you're going to use either the average or the median. You're going to use mean or median, right? Those are the two numbers that you use. When do you use the mode? That's kind of a hint because I said numbers. So when do you use the mode as the most frequently repeating value?
When you can't use the other two.
When you can't use the other two, exactly. So if your data is qualitative, i.e. it's nominal or it's ordinal. So if you're talking about data that said, oh, what color hair do you have? Can you calculate the average color of hair? No, but you can figure out what is the most common color of hair, which one repeats the most frequently, and that's the average that you use for that particular piece of data. So data that is categorical tends to be reported in a mode base because that's the most common. All right? And again, just to reiterate, when your data is skewed, remember we talked about skewed data back in chapter 2. So when data is skewed, you have a tail of data that offsets where the mean normally would be. Normal data, when your data is uniform or normal, the mean and the median are together. When you have skews of data off on either side, it will pull the data away from the median so that the mean and the median will be different. So again, remember that those pictures we were playing around with when it came to skewed data. Normally, you would say in this data set that the mean and the median should pretty much be right here. That's where you would want it to be, because most of the data is sort of bunched right around that central hump of information. The problem with it, though, is when you have a skewed tail, right? The median will stay where it's at. The median will stay basically in the middle, but the mean will get offset. And it will be skewed to the right. Yeah, those are the zeros. Yeah, skewing me off to the right. If you think about a little graph, if you thought about a bar graph of my data with quiz scores, most of the quiz scores were right up there at 6, 5, and 4, but then I had a few 3s, a few 2s, a few 1s, and an unhealthy number of zeros that brought my average or my mean way further off to that side, and that's why the mean and the median were so separated, all right? And so skewed data is definitely something you want to know about, because it definitely can drive data to a different conclusion. So if your data is uniform, so again, think of these things as being frequency and data. And I don't even need to put numbers on this necessarily, just giving you the idea. Basically, when the data is nice and uniform, your mean and your median will basically be right next to each other, okay? And again, that tells you something about the data. So when someone gives you both the mean and the median, you can say, is this data skewed versus is it normal or uniform potentially, right? I mean, that sort of information is good information to know about the data, right? So that you can't be misled by one or two different numbers. All right. Good with mean, median, mode? Okay, I don't want to spend too much time on it because it's the sort of thing where you've probably dealt with those three before at least one point in time in your life. All right, so perhaps the more fun topic. Measures of dispersion. First off, what does it mean to have data that is dispersed? What does dispersion mean?
Spread out.
Yeah. So how spread out is your data? Or how dispersed is your data? It's unfair to use the word dispersed to define dispersion, but it makes it easier. The first classic measure of dispersion is the range. How do you find the range of a set of numbers?
Big number next.
That's the simplest measure of dispersion that you can get, is just taking the largest minus the smallest. So how else do you think you might figure out how dispersed your data is? So one of the things that you may try and do is to try and figure out how far away your data is from the middle, right? So one standard thing that we would think to try and do this dispersion, if I can spell the word. How far data is from the middle. Now, what are we going to call the middle? Well, in this particular instance, let's try and use the average, or the mean, if you will. So let's look at a set of numbers. Let's look just at a small set of numbers. Let's say, let's suppose our data is 1, 7, 8, 11, and 13. So first off, for those 5 numbers, what's the average? Or what's the mean?
8.
Did it really work out to be 8? 20 and 20 is 40 divided by 5 is 8. Okay. Conveniently enough, it's the mean and the median. Pardon me. This is supposed to be the mean. All right. So now, what's the difference between the data and the mean? Difference between data in other words, how far is it from 1 to 8? How far is it from 7 to 8? How far is it from 8 to 8? Now subtract the opposite direction. What's 8 minus 11? And what's 8 minus 13? What happens when you add all of those numbers up?
You get a zero.
Why?
Because you minus your 5, then gives you 2, and then 2 plus 1 is negative 3, 3 and negative 3 is 0.
Yeah, because you've got 8 positive numbers and 8 negative numbers, so 8 and negative 8, 0. Does it always happen like that, or was that just because of the numbers I picked? Should I pick 5 different numbers and see if it works for those?
That's your number 3.
Always.
It's always going to do it. Why does it always do that? Yes.
All those numbers, so it's taking it from
Yes, that's absolutely right. This is actually an alternative definition to the mean. So the sort of way we've learned to calculate the mean is by adding up numbers and dividing by numbers. If you learn about some history of mathematics, the way they used to teach students how to find the mean was not by calculating it by adding numbers and dividing. They actually said, hey, find the one point such that it's the same distance from that point to all the points to the right of it as it is to all of the points to the left of it. They actually did it as a visual problem more than a calculation problem. Mean used to be a visual concept because it was easier to think about terms or ideas in terms of pictures instead of a bunch of added numbers, okay? We, of the computer generation or the calculator generation, we are a lot more comfortable with adding a bunch of numbers up and saying, I know that that sum of numbers is correct because we trust the calculator that does it for us. Back in the 1800s, if they had 3,000 numbers and they had to add them together, they didn't trust the sum. Instead, what they would trust is their sight that could say, hey, this is the one number where the distance to all of these and the distance to all of those is going to be the same. They balance each other out. And that's essentially what they're doing, is balancing. And making sure that it's always balanced. Which is relatively interesting. So the problem then comes, well, these numbers are good numbers. How do we deal with it, right? So the first mathematician that came along to this problem said, well, I don't want these numbers to cancel out. How can I change these numbers so that they'll quit canceling each other out? What's the really simple, what was that?
Throw some absolute value in and make those negatives positive.
Yeah, throw away the minus signs. Quit thinking of it in terms of minus signs and just look at these as absolute values, right? So look at these numbers as 7, 1, 3, and 5 instead of negative 3 and negative 5. And what mathematicians discovered is that if you just throw away the negative sign, the problem with it, and bear with me, I'm going to do a little bit of algebra here for you guys. When you're graphing the absolute value of a number, so again, quick root. When x is 3, folks, what is the absolute value of 3? 3. When x is 2, what's y? When x is 1, y is 1. When x is 0, y is. When x is negative 1, 1. Throwing away the negative signs. And the reason why this is a problem mathematically is that when you graph this line, what does it look like? Yeah. It's actually a V. It makes a point. When you're dealing with mathematical calculations, this
is what a mathematician would call a point of singularity. It's a discontinuous first derivative. Again, don't worry about the mathy side of this. But the idea is that this is the equivalent of having a black hole in your math. If you have a black hole, folks, life is bad, okay? So this doesn't work, okay? So what we need is something that is not a point and is instead a nice smooth graph. And so instead of taking the absolute value of these signs, the next easiest mathematical construct that you can do is to square all of these numbers. Because what happens when you square a negative number? What's negative 3 times negative 3? A positive 9. Okay, so what mathematicians discovered, and it was sort of a joint relationship between math and statistics. If you square the numbers, math is smooth and can be analyzed. Basically what I'm doing here for you folks is I am skipping 2 weeks of math to explain why we square to calculate the standard deviation, okay? The simple explanation is this point causes a problem. The math behind it is very complicated, and I don't want to confuse you with way more math than you need for this class. But the fact remains is that when you square the data is actually analytical and can be studied on a level that most mathematicians are comfortable with, and so it's okay, all right? So what we do we use the square of the difference between our data and the mean to compute the variance of our data. And so here's the first term that we use for measuring dispersion. Variance and it's calculated through the square of our data. And I'm going to write it mathematically first. And we use this to calculate the variance for a population of data. If, on the other hand, you are dealing with a sample, you actually take one less than the number of numbers when you are working with a sample. All right, now, I'll speak next class about what the difference between those two is a little bit, just so that you can get used to it. But the idea is that we're using these values to calculate variance. All right, now, a little extra piece of information to go with it. One of the things that you have to get used to when you're dealing with statistics is when do you use Greek versus when do you not use Greek. Okay? When you are working on a population level parameter, you will use Greek. So note, this is called sigma squared. This is a lowercase sigma. The capital E is the uppercase sigma. When you are dealing with a sample, we switch back into English. You use a regular S to represent the sample variance, or S squared to represent the variance of a sample as opposed to the variance of a population. Okay? We'll be doing this a lot throughout the rest of the semester, but it's one of those things that you kind of got to get into the habit of noticing and using whenever you get a chance. If you're talking about populations, use Greek letters. If you're talking about samples, use English letters. All right? So similarly, have you guys seen the Greek mu before? We're going to be using this a lot as we move along. So since I'm in this stage of talking about the difference between Greek and English, population and sample, you kind of got to get in the habit right now of dealing with it so that when you talk about populations, you use Greek. When you talk about samples, you use English. I should have probably stressed this back when we were talking about populations and samples back in chapter 1, but I forgot. Sorry. So I'm going to try and focus on it right now so that you guys know that this is something you have to get in the habit of understanding when things are written down and used in statistics, okay? All right, so I don't have that much time left. Okay, so really quickly, so the cool part about this measure of dispersion, variance, notice how I described variance as sigma squared or S squared. I kept the squared in there because we squared the difference between each of our data points and the mean. When you want to get out of a squared measurement, you need to take the square root. And when you take the square root, you'll switch into calling it the standard deviation instead of the variance. Okay? So, if you are asked to tell me what the standard deviation of a population is, it is the square root of sigma squared. What is the square root of a square? Just sigma by itself. And then likewise, if you take the standard deviation of a sample, it's the square root of S squared. Square root of a square gets you back to S. All right, so that's all. Most of that is just getting you into the first round of notation for these sorts of calculations. I will try and be explicit when I write these things down for the next week or two. But after we've gone about doing this for a week or two, I am just going to write down S and assume that you guys know that I am talking about sample standard deviation. And when I write down sigma squared, you guys know I'm talking about population variance. Okay? These are the sorts of things that you kind of have to get into the flow of hearing and translating so that you use the right variables and the right letters at the right time. And it is very standard throughout the entire industry, okay? If somebody's reporting about the standard deviation of their sample, they are gonna call it S. That's what they're gonna call it, because that's the standard that everyone has been using for the last 60 to 70 some odd years, okay? So, let's do some calculation again. I sort of got carried away a little bit. So, find variance and standard deviation for sample data of 4, 6, 7, 8, 12. Oh, I don't want to make it nasty. Does that work? What does that add up to? 44?
10, 17, 25,
54? 54? I want something divisible by 6. That works, right? Okay. Something relatively straightforward. Okay, so let's find the variance of standard deviation for this sample data. Okay? This is sample data. So how am I going to calculate the standard deviation? Well, what do I have to do first? Find the mean is always the first step. Whenever you're calculating standard deviation or variance, you got to find the mean first. So I was trying to make sure that it worked out nicely so that the numbers weren't really scary. So 54 divided by 6, 9, right? Now, I want to find the sample variance. That's S squared, which is the sum of x minus x bar squared all over n minus 1. So now how do I do this weird x sub I minus x bar squared thing? What is my first number, folks? 4. Yeah, 4. 4 is my first number. What is 4 minus 9? What's my next number? You do each one down the line, exactly. So my next number is 6. What's 6 minus 9? Don't forget that you're squaring it, right? So that all those negatives are going to go away. And then just keep going down the line, right? What's 7 minus 9? What's 8 minus 9? What's 12 minus 9? And last but not least, 17 minus 9. And what am I going to divide by? How many numbers are there? So what is negative 5 squared? Add them up. 30, 48, 112. So your standard deviation for this set, or your variance, your sample variance for this data is 22.4. What's your standard deviation? Exactly. General rule of thumb, folks, whenever you're calculating the standard deviation, go one more decimal point than whatever your mean was calculated to. So note, our mean was rounded to 9. What is my standard deviation? Take the square root of that, round it to one decimal place. .7. So calculating standard deviation is just a process of following the steps in this math formula, right? Take each of your data set elements, subtract the mean, square it. Move to the next one, do the same thing, add it up while you're going. Once you have added them all up, divide by the number of numbers minus 1. Again, when you're working with a sample, take 1 less than the number of numbers. If you're working with a population, don't take the n minus 1, just use n, okay? And there's about a 2-week explanation for the difference between those two that I'll give you in about 5 minutes on Wednesday. I'll try to condense it as much as I possibly can so that you can sort of see where we're going, but you don't necessarily have to get the huge mathematical problem that mathematicians use to show this and why it's of importance to us when we need to calculate it. Even the math behind this was literally 2 weeks of math, and I don't want to kill you guys with it because it was really painful even for me, and I supposedly understood it. And a lot of it was just like, whoa, again? Here we go. So anyways, when we come back on Wednesday, we will spend a little bit more time calculating variances and standard deviations and trying to get comfortable with the calculation side of this. I will also tell you folks that there are ways to do these calculations using calculators that make it very easy, as well as using spreadsheet programs that make it, 5 clicks and you're done. Okay, and after we have done a little bit of practice doing it by hand, I will show you how to do it using calculators and or computers, all right? So, it's a good spot to stop because it sort of got you into standard deviation and variance, but not far enough that we can't repeat it next class. Thank you.